So, nuclear stability. So this first slide talks about transuranic elements and radioactivity. So first of all, what does the term transuranic element mean? Found after uranium. So if you're looking at the periodic table, everything after uranium is considered a transuranic element. The reason why it has a specific category is because if you look, especially at this periodic table, the periodic table that we have here in the classroom, you'll notice that the elements have different colors, like some are white, some are black, some are blue, some are red. Why are these, can anyone give me a guess as to why the red ones are red? Yeah, the gas is at standard pressure and temperature. So what are the black ones? Solids at standard pressure and temperature. So what are the blue ones? Liquids at standard pressure and temperature. So what are the white ones? Sort of.
Man-made.
Yeah, they're man-made. We haven't found them in nature. So if you'll notice, with the exception of number 43, everything after uranium is white. And I guess technically it's white. So you'll notice that the stuff written in white also has like parentheses around that atomic mass number at the bottom. Because that atomic mass number is supposed to be kind of like an average of all the isotopes that are found in nature, but if we don't find it in nature, you can't really have an average. And the theory goes, and this is kind of an old periodic table, nowadays we have at least up to, 118? Not only found, but named. So like here, these you see that says like UN, UUUUUV. Like those are just unnamed. Well, they were unnamed at the time of that thing's making. So when you're looking at that, all the white stuff is just stuff that we've been able to make in the lab. So that's the first thing to know about transuranic elements. They just don't occur in nature. Now, that doesn't mean that they aren't created naturally. It just means that they're so radioactive that they just don't last very long. And pretty much the only reason why we have most of the elements past iron, that's a little extreme. Most of the elements up to number 88 probably, or up to lead maybe. The reason why we have most of those elements and they haven't like all radioactively decayed is because uranium decays into pretty much everything up to lead. So where is lead on that periodic table? 82, it's peanut butter. Eventually, given enough time, uranium will decay into lead. But the question is, how much time is enough time? Well, that's one of the things we talked about with half-life. Basically, half-life is how long it takes half of the sample to decay. The half-life of uranium is 4.5 billion years. Which is really interesting because, for instance, we think the sun is only about 5 billion years old. Matter of fact, we think the universe is only about 13.7 billion years old. So, uranium tends to last a while. And as it decays, it tends to turn into, well, basically all of the elements in between uranium and lead. So that's the reason we have most of those things hanging around, is because uranium's just decayed into it. So again, that's transuranic element. All of these elements past uranium have a high amount of neutrons in the nuclei and tend to be unstable. At some point, this makes a neutron will decay, making the element radioactive. And sometimes this decay happens over millennia. So again, uranium. Most radioactive places on Earth. We'll probably look at that, but that's not right now. So, radioactive decay. When Marie Curie did her research, she identified 3 types of decays. She had alpha decay, beta decay, and gamma decay. And again, they're called alpha, beta, and gamma because that is the order she discovered them. Because those are the first 3 letters of the Greek alphabet. So what is alpha decay? It's when the nucleus falls apart and actually spits out an alpha particle, which is really just a helium nucleus. It's 2 protons, 2 neutrons stuck together, get spit out of the nucleus. It's actually the most dangerous form of radiation, but it's very easy to block it. You can just literally a piece of notebook paper is all you need to block out particles. The reason why it's the most dangerous is because they travel fast, usually like 20,000 meters per second, which is pretty good speed. And they're pretty big considering, like beta is an electron. So helium nuclei, that's pretty big compared to just an electron. So it's traveling pretty fast, it's pretty big, so it has a lot of, quote, momentum. And therefore, when it hits your cells, it can do the most damage, right? Just think of like a tank shell versus like a bullet from a gun. Like the tank shell is going to do far more damage. But unlike a tank shell, it's super easy to block it. Because it's so big, like it doesn't go through most things. Pretty much that's what we're trying to do when we block radioactivity is we need something to either absorb it or deflect it. Now, and the fact that this is an alpha particle, since it's so big, even something as thin as a sheet of paper, the odds of it being able to make it through the sheet of paper are basically zero. Because there's just going to be so many atoms, even though those atoms are mostly just empty space. So alpha decay is, again, it's definitely the most dangerous type of radiation, but it's also the easiest to block. Beta decay, there's 2 types of beta decay. There's beta minus, where a neutron decays into a proton. I know this doesn't make a whole lot of sense at this point, but we'll get to some explanation. Right now I'm just giving you the definitions of these. So beta minus decay is where a neutron turns into a proton. Well, due to the law of conservation of charge, neutrons are neutral, and if it becomes a proton, well then a negative charge must be created as well. And so the neutron decays into a proton, and a beta minus particle, or an electron, is shot out of the nucleus, because electrons don't hang out in the nucleus. A beta plus decay, this is where a proton decays into a neutron. And again, you have a positive charge, and now you have no charge. Well, then a beta plus particle, or positron, is emitted. So again, that's our piece of antimatter we talked about earlier. You can block this with a sheet of aluminum. Probably not aluminum foil, maybe something a little bit thicker. But again, it's going to be something where we're going to have something that can interact with those electrons. Since again, the electrons are smaller, we need a little bit more layering, a little bit more thickness to make sure something hits. And then we come to gamma decay. Gamma is not a particle, it's actually just a gamma ray, like a piece of our electromagnetic radiation. Gamma ray photons are emitted, usually after other forms of decay have taken place. They can be blocked with a good chunk of lead, like 6 inches of lead. Because again, they're very high energy, it's difficult for things to interact with it. So, it says it usually takes place after other decays, so we'll kind of get into that later. So a lot of times when you see like, oh, this thing's going to decay, it'll make a beta and, let's say beta minus, and then a gamma ray. It's because of the excitation levels. And then transmutation. The definition of transmutation is the transformation of one element into another by radioactive decay, nuclear bombardment, or a similar process. The word transmutation was coined literally because when scientists figured out that, say, like uranium was decaying into other elements, we already have a word for this. It's called alchemy. And when they figured it out, they were like, oh, we're observing alchemy. And one of the scientists, it was like Richard Soddy and I forget the other one. I think Soddy was just like, don't call it alchemy, don't call it alchemy. Call it anything else, don't call it alchemy. Because that's like witchcraft. So, transmutation, not alchemy, because that's witchcraft. So transmutation, so this is again alpha decay. So for instance, uranium, this is uranium-238. It's our most common form of uranium, has 92 protons and 146 neutrons. If you just let it sit there long enough, it could decay, long enough, like 4.5 billion years. It could decay into thorium and a helium nuclide. So this would be thorium plus an alpha particle. So if you look here at our reaction equation, first of all, this should look oddly familiar, like chemistry. It's not that bad, really. But I will give you some equations like this, and I might just say, like, uranium decays into blank plus an alpha particle. So in that case, you have to know what an alpha particle is. But really, if you know what an alpha particle is, you know, okay, this is uranium, and it has this alpha particle has 2 protons. Well, you subtract 2 protons from this, it obviously has to be thorium. Like, there's literally nothing else. It's not as bad as y'all think, and I know, because I remember chemistry and it being a nightmare. You're going to wish all your chemistry stuff was like this. So again here, this kind of shows different things that can be blocked. So we have alpha, beta, and gamma, but we can also throw in X-rays there. So you can discover X-rays, but again, X-rays are a type of radiation. And then you should also note that the neutron is actually one of the hardest things to stop. And it's the hardest thing to stop because, like, you know, alpha particles are probably going to hit something. Beta particles are probably going to hit or get repelled by the electrons, the other electrons in the material. But again, they're smaller, so they're harder to deflect. X-rays and gamma rays, you just have to put enough stuff in there that they're likely to get absorbed, right? They're just a photon. And they'll probably be re-emitted, but at something of lower frequency, so they're not as dangerous. But the neutron, because it's neutral, doesn't really interact with anything. So it's really difficult to stop neutrons. And so here, we talk about stopping neutrons with something like, 6 inches of water or something. It's water, if you guys don't know this, water is actually really dense. So here's an example of some radioactive decay equations. So we can kind of work these together if y'all want. Like I said, it's really not that bad. So for instance, it says we have Cm 96. What the heck is Cm? It's number 96. It's named after Marie Curie. It's curium, I think. Like californium is number 98. So we've got this one, and this puts off He2. What do we call this thing? That's an alpha particle, right? So we're going to lose 2 protons. So this thing over here, how many protons should it have? 94. So then we look at our periodic table. What's number 94? Poo. That's plutonium. The plutonium. So now we have to write down the number of nucleons inside there. So how many came out? Well, 2 protons came out. How many total nucleons? 4, not neutrons. So 4, so it's 247 minus 4. 243. That's it.
What do you mean by nucleon?
Things that are in the nucleus.
Okay.
So that would be protons plus neutrons, right? Because we had 2 protons come out, but we also had 2 neutrons come out. So that's 4, right? 4. And so 7 minus 4 is 3, right? Question.
How do we know the 2 neutrons?
Well, it's right here. It's part of our alpha particle.
Oh, okay.
Because our helium nucleus has 2 protons, and it's got 4 things in the nucleus, so the other 2 must be right. All right. So now let's look at beta decay. So beta decay, it says this is 257 FM 100. So FM 100. So what that is, Frank? I forget. It's named after a scientist, but not a chemist. Might be named after Faraday, but I don't know. I can't remember. So anyways, we have this thing and an electron come out. So first of all, this would be called beta minus decay. And I want to point this out because I might just give you it with beta minus decay and not the electron thing. So we should know both of those things. So what did it say for beta minus decay? What turns into what? Okay, so I'm going to write that over here. Beta minus, neutron becomes proton, right?
Yep.
So in this case, how many protons did I start with? 100. So one of these neutrons becomes a proton. So how many protons do I have now? 1. So what's 101 on there? MD Mendelevium, which is hilarious when you think about it, because it's actually named after Mendeleev, the guy who invented the periodic table. And he didn't get an element until 101? Really? You want to Einstein for you want to never mind. Okay. But how many nucleons, how many things are left in the nucleus? It's the same number. Still 257. Because a neutron becomes a proton, but it doesn't leave the nucleus. It's still there. So it's still 257. So the math is actually really easy for beta, right? You're like, oh, add ones. But it should be noted that like it didn't just magically come from anywhere, it just neutron became a proton. Okay. And then last but not least, gamma decay. So here it says we have uranium-235, has 92 protons. So gamma, again, I could just write gamma decay, but it's just going to be a photon. What does it become? Well, did any protons come out? No, so this should be number 92, right? That's still uranium. Did any neutrons come out? Nope. Bang.
What?
What?
That's not.
Okay, but so this is where the confusion comes in, because I feel like, I think it's in these notes, but I feel like if you just, because this is the level I'm supposed to teach it to you at, this doesn't make any sense. But this is the correct answer. Okay. So first of all, this is the correct answer. Second of all, let's talk about why, because that doesn't seem to make any sense. So here's the answer. That's what we got, right? Okay. Let me double check something, make sure it's actually in these notes here. Yes, it is. So we will get to the answer. We're just going to delay it for a minute. All right. But I want you to hold on to that question. I'm glad that it bothers you guys. Come on. All right. Well, come on, man. Okay. Radioactive half-life. So here we've made mention of half-life before, and this chart actually is for uranium itself. You could do this for pretty much anything else, although uranium has a very interesting half-life timetable here. So the half-life of radioactive elements is the time required for half the material to decay. So basically, I need to be on the next slide here. If we have a graph of time and a number of atoms, like literally, okay, this could be like 100 atoms, right? This thing will asymptotically approach zero. Problem with that is that mathematically, this is never zero. So you can't ever be like, when does it all decay? The answer is never. But what they figured out is that at some point it will definitely hit 50, like half of what it started. And this time right here, that's the half-life. It's literally the time it would take half of it to decay. Make sense? Because on these exponential decays, like we can easily make them, but then they never have an end. So essentially what we say is that once you get 10 half-lives, the thing is basically dead, right? Because basically, if you go down 50 for the first one, how many would it have after the second one? 25, then how much after the third one? 12 and a half, I guess. Not possible, but that's after 1, 2. This is the second one, this is the third one, right? So after 3, you'd have 6, roughly. And then 3, I mean, when you start with 100, when you hit like 3, you're like, okay, there's not a whole lot left here. But still, that's only like 4 or 5 half-lives. So again, if you double that, basically everything should be gone by that point. So here, this particular chart over here shows the half-life of uranium. So like uranium undergoes alpha decay, it becomes thorium-234. then it undergoes a beta decay to become protactinium, then undergoes another beta decay to become uranium, and then it lists the half-life for all of these. So like the half-life for uranium just to become thorium is 4.5 billion years. But some of these are a little shorter, like this one here is 1.5 times 10 to the negative fourth seconds. What's really interesting is if you look at this, it goes like uranium, thorium, protactinium, back to uranium, thorium again, radium, radon, which is a deadly gas, polonium, lead, bismuth, polonium again, lead again, bismuth again, polonium a third time, and then lead a third time. Man, mystical journey. Okay. That's a lot of crazy stuff. And like I said, some of it takes years and years, but then theoretically, lead 206 we find to be completely stable. Right? So eventually, uranium becomes lead, but that's kind of glossing over everything between.
Some detours in there.
But you have to understand, when people started researching this, they were researching like uranium, and like a chunk of uranium has like all of this stuff in it. And so when Marie Curie started doing her experiments, she was trying to separate all of this stuff from each other, and it just so happened that radium just glows green all the time because it's giving off radiation. So here are other elements and their isotopes, and again, in the natural processes, if you kind of take them all together, most processes don't really favor producing, let's say, hydrogen-3, or what is this, tritium? No, that's deuterium. They essentially don't favor making one over the other, but over time, because this is like, say, a radioactive form, there's just going to be less of it around, because it'll decay into something else. And so here you can see like different elements, their isotope form that we're particularly talking about, and then the half-life. And so you'll notice that like carbon-14 becomes, nitrogen in about 6,000 years. So what's interesting is that's how carbon dating works. You're not taking carbon out for lunch. What you're doing is you're looking at organic compounds, and like we're organic compounds here on Earth. Pretty much everything is what we call a carbon-based life form here on Earth. And so that means we use carbon to build our cells, which is why you take OChem or organic chemistry. It's all about carbon. But the deal is that if you look at things that died long ago, you'll find basically nitrogen where carbon should be. And that's where you go, how did nitrogen get in there? Like nitrogen doesn't work like that. And then you realize like it used to be carbon-14, which decayed into nitrogen, but it takes almost 6,000 years. And so since we know the half-life curve of carbon-14, we can basically go in and count the number of nitrogens that are where carbon should be, and that's how we can estimate the age of fossils. Right? Now again, if the fossil is significantly older, more than 10 times this number, well, carbon dating is not going to work. Right? So anything older than 60,000 years, we can't really use carbon dating. No, that's not right. Anyways, and then last but not least, this column just shows you what type of radiation is produced. So atomic mass unit, unified atomic mass unit, it's based on carbon-12, okay? So the symbol is U, so 1 U is equal to 1/12 the mass of your carbon-12 atom. Does that make sense? This is important for the calculations that are to follow. You were probably told this in chemistry, but you never really dived into it, so it didn't matter. Since the unified atomic mass unit is based on carbon-12, the mass of one proton is slightly more than one atomic mass unit. So in chemistry, you were told, first of all, that a neutron and a proton have basically the same mass, right? Or maybe you were just straight told they have the same mass. They don't. Protons and neutrons are slightly different. Neutrons are slightly heavier. But, if you round it to like 2 decimal places, then they're the same, right? So we define an atomic mass unit to be just the mass of a proton. But again, we didn't define it on hydrogen, we defined it on carbon. As a result, our atomic mass unit ends up being slightly slightly smaller than an actual proton. What does this all mean? Well, so right now, it means that the mass of a proton is slightly more than one atomic mass unit, according to our definitions. That makes sense? And the neutron's a bit more than that, right? So when I first heard this, first of all, I got a little upset that they weren't the same, because people had told me they were the same. But second of all, the longer I think about it, the more I'm like, well, actually, I like that because I don't like the fact that different things have the exact same mass. I mean, you can be similar, like, it's like you and your classmates. Like, oh, yeah, we all have similar masses, maybe. But if you have the exact same mass, that's just kind of weird, actually. So, this brings us to our nice, fun nuclear stability charts. Don't worry, I'm giving you pieces, and we'll put the pieces together here in a minute. Because hopefully me stating that last slide gave you some more questions. Here, this is nuclear stability. This is what we're trying to get at in these notes here. So across the bottom of my graph, I have the proton number, usually called Z. That's the number of protons in your element, right? And across the y-axis, we have the number of neutrons. So at first, for low numbers of elements, you have basically the same number of protons and neutrons, right? Like oxygen has 8 protons, 8 neutrons, typically. Now, what you'll see here is everything in blue and red. So every dot on this graph represents an element that we've either made or found, an isotope of particular element. So like one line here corresponds to very specifically one amount of protons, right? So that's one particular element. But notice like all of and these are not lines. These are just individual dots, which is why some of them are broken up. Those are elements that we found, but they just have different numbers of neutrons. And so things on top here have more protons than neutrons, and things below have the same number of protons as neutrons. So first of all, you'll see 2 lines on this graph. You'll see the Z equals N line. That's the line that you see if you have the same number of protons as neutrons, right? So at first, they're basically identical. And then what you have here, the second line, is actually the line of stability. And so you'll notice that at first, you need the same number of neutrons as protons, but as you crank more protons in there, you get up to this point here where you need more more neutrons to be stable. But you gotta feel like I already know that, right? And this goes all the way up to bismuth number 83. And that's an important thing. Bismuth, I'm not gonna quiz you over it. Bismuth is theoretically the last stable element that we know of. Basically, everything else we've found past bismuth, given enough time, will radioactively decay. And again, the stuff like francium and radon are only around because uranium decayed into them. Does that make sense? So since uranium is still around, like way out here, it's still creating these other elements back to bismuth. So what you're seeing here is everything written in blue. These blue dots are stable nuclear configurations. If the atom is not in one of those stable configurations, well, it will eventually decay into something else to make it more stable. And that's the whole deal. Like these atoms, these nuclei are trying to quote, roll downhill. They're trying to get to their lowest energy state, okay? So for instance, and that kind of explains what we saw with uranium earlier, like it might decay into lead, which is like right here, but if it decays, let's say, above this blue dot here, like it's up here, it's still not stable. Whereas maybe then it'll lose an alpha particle and drop down to, but maybe it drops down, now it's down here or something, and then it has to, go back up. And so what's happening here is that the elements are trying to get to the stable line as far as we can tell, right? And so again, anything that has a blue dot is a stable isotope. Anything that's a red dot is an unstable or radioactive isotope. Does that make sense? So here it says unstable nuclei on bands on both sides of stability. Stable nuclei cluster very close to the line of stability. And to say about that right now. Do you have any questions? Because there's more here, I'm trying to go in the order that I put it on here. So graphically, the stable nuclei cluster very close to the line of stability. There are no stable nuclei greater than bismuth, at least that we found right now. Heavier elements up to uranium are found in nature, but again, they're all radioactive. Unstable nuclei are the bands along the sides of stability. The lightest elements with Z less than 16 are stable approximately when the number of neutrons is equal to the number of protons, right? So basically anything less than number 16, which is strong? Yeah. Yeah, because silver? Sulfur. Oh, okay, sulfur. I'm like, that's not sulfur. Okay, so sulfur. So you'll notice that sulfur has 16, but it has 32 nuclei. Okay, silicon, anyway. As the number of protons increases, the number of neutrons generally grows increasingly larger than the number of protons. Because again, the protons don't really want to be hanging out near each other because of the electromagnetic force. But again, if you cram enough neutrons in there, we get stability, seemingly up to number 83. Now, I will tell you a secret that chemicists or high energy physicists, whatever you want to call them, do predict another island of stability. Like way out there, like I think element number 125 or something is supposed to be stable, but we haven't seen it. And we haven't made it. But maybe one day it'll get there. And maybe it'll be stable. That'd be cool. All right, so let's talk a little bit more. So this graph here is just a sketch of that graph we saw earlier. Does that make sense? So here, beta decay. So we have two types of beta decay. I think alpha is pretty straightforward. You lose a chunk. Alpha decay, basically, you lose that chunk because it's just too big and the strong nuclear force can't hold it. So by losing a chunk, it'll like kind of reconfigure and make it a little bit more solid, right? So now let's talk a little bit about why the heck a proton would become a neutron, or a neutron would become a proton in the first place. So here, we have like X and Y as just representing generic elements. And A is the number of nucleons, right? Things in the nucleus. Z is obviously the number of protons, right? So generically, if you wanted to write a generic formula for beta decay, so you say you have element X, it decays into element Y with a beta minus, but plus energy. Okay, that's one of the things, is giving off energy, becoming more stable, like a ball rolling downhill. When the ball gets to the bottom of the hill, it has less energy. Make sense? It's more stable. So in this case, our neutron becomes a proton and emits an electron plus energy. So you can kind of think of it, because it's kind of weird to just be like energy. You can kind of think of like the electron's going to shoot out of there with some kinetic energy, right? Which then if the electron hits something, then maybe it gives off a photon. That makes sense. But we say energy because we don't know, and depending on the thing, you don't know exactly how much kinetic energy this thing come out with. And we can get into that in a little bit. And then beta minus is essentially a proton becomes a neutron. So again, like A stays exactly the same. And here, our number of protons decrease. But again, a positron comes out plus energy. So again, it's kind of like the electron's shooting out of there. The positron's going to shoot out with some kinetic energy, right? So it says nuclei with excess neutrons can become more stable by beta minus decay. And then nuclei with excess protons, which is less common, can become more stable by beta plus decay. So on that line of stability there, if you're looking at stuff that's above the line and below the line, the stuff above the line can become more stable through beta minus decay. So pretty much everything up here that's above that blue area will eventually undergo beta minus decay to become more stable. Either that or possibly alpha decay. And then the stuff below the line is beta plus decay. And what you should have noticed is that there's more stuff above the line than below the line, so positrons are a lot less common than electrons in that case. I think this is a really neat chart because you can see different types of decay on it. Example 2, your body contains several radioactive isotopes. Approximately 20% of this radiation dose you receive each year comes from the radioactive decay of these atoms. So out of the yearly dose of radiation your body receives, approximately 20% is self-inflicted. Because you eat stuff that's radioactive. Stop doing that. So most of this dose comes from one potassium isotope, potassium 40. So out of the 20% that you give yourself, most of it comes from potassium, which you need. So good luck with that. Which most commonly decays by beta minus emission. What is the daughter nucleus? Okay, so when it comes to radioactive decay, we call them like mothers and daughters, mostly because men can't give birth. Because you keep a daughter, then a daughter can have another daughter, right? So it commonly decays by beta minus emissions. What is the daughter nucleus? So if we're looking at this, so let's write this down. So we have potassium 40. How many protons should potassium have? 40. Ooh, 19. 19. All right, so it's going to decay by beta minus, so beta minus, or electron, right? Everyone say it. Plus something. What is this daughter? So that's the question. So what happens to this 19 through beta minus? What happens to beta minus? Blank becomes a blank.
Neutron becomes a proton.
Yeah, neutron becomes a proton. So 19 becomes what? 20. What happens to 40? What is 40? So what has 20 and 40? Calcium. So that's a daughter nucleus. Calcium. Cool. Now if you look at calcium, the more common form of calcium does have 40 nucleons. So that's probably pretty safe. So it's probably just potassium just decays with once. Plus energy. Not really.
Okay.
No. I know what y'all think because y'all had to do that in chemistry, but that is not. This is not like an endothermic exothermic reaction. Because at the end of these notes here, I'm going to kind of explain that stuff I was talking about earlier, like what the heck's going on with gamma. And you'll see why we're not going to calculate it. Okay, but you are going to calculate this stuff. The binding energy. So, this is one thing that should be gnawing at your brain right now. We haven't got to gamma yet, and exactly what's going on there. But this is what I said earlier about how when we define how much a proton is and why it's not exactly one, that actually leads to some interesting things. So nuclear binding energy is how much energy it takes to hold the nucleus together. It's computed by considering the mass difference between the atom and its separate components. In this case, hydrogen, atoms, and neutrons. So it says hydrogen atoms. That's literally what we're talking about. But you can think about it as protons. Okay. So here's the deal, and this is something that is totally covered in your chemistry class. And your chemistry teacher probably glossed over it. Even if they knew what was going on, they probably deliberately glossed over it. Because, in chemistry, just look at it. If you just look at hydrogen and helium, what's in the nucleus of your helium atom? 2 protons and 2 neutrons, right? Hydrogen is what? What's in the nucleus of that? Pretty much just 1 proton. It could have more than 1, but again, its average nucleon number is 1. What's interesting here is that you see it has like that atomic mass at the bottom, the 1.00794. That's that thing that we talked about earlier. But I said it's not exactly 1 because it's based off of carbon 12. But what's interesting is if you just straight up take that number and you just assume that all neutrons and protons have the same mass. If you take 1.00794 times 4, because it's 4 over here, do you get that number, that 4.00260? No. You don't. Even if you correct for the correct protons and neutrons, you don't get that number. And that's what's happening here. is if you're calculating the binding energy, P, you're going to take the number of protons, Z, times the mass of a hydrogen atom. Y'all see that? The number of protons, and this is for any element. Take Z, number of protons, times the mass of a hydrogen atom, which, is given here, there, and on your equation sheet, plus the number of neutrons, N, times the mass of a neutron. Then you subtract out the mass of the atom. That will give you what is called the mass defect. And then you take that and you multiply by 9.3149 mega electron volts per atomic unit. And that will give you what's called a binding energy. So let's break this down here. So first of all, this first part here is saying, okay, I have, let's say, 10 protons. Well, if I have 10 protons and each proton has this much mass, I should have this much mass because of the protons, right? Then I do the same thing with the neutrons, and I should have this much mass because of the neutrons. And I add that together, that's the total mass this particular atom should have. But then I go to my periodic table and I look at the atomic mass unit that it actually has. And we subtract those two numbers. And when we do that, we get a difference. It's called a mass defect. And so here, that's what we see in this example. So for hydrogen, you have 2 protons, right? And then you have 2 neutrons. So you multiply that times your proton mass, 2 times your neutron mass, you get these two numbers. You add them together, you get 4.03298. And then you compare that to what it actually says it has, 4.00260. So if you look, that's the 4.00260. And so this is the mass it should have mathematically, right? If I got 4 protons, they don't magically change mass, or do they? So then this is what it actually has. So you subtract the two, you get this mass difference. It's called mass defect. Basically, it should have this mass, but it doesn't. Is that right with me? Then we multiply that times this random number to get the binding energy. Okay. So I'll explain the random number, but does everyone understand this calculation? It should not be difficult, and sometimes the questions will ask you to calculate the binding energy. Sometimes they'll ask you to calculate the binding energy and do something with it, or sometimes they'll just ask you to calculate the mass defect, which essentially means you don't have to do this. Here's the deal. This thing right here, this 9.31.49 is actually, with the proper units, this is mega electron volts per atomic mass unit. In a different, you guys would actually recognize that number if I changed the units. If I changed the units from mega electron volts per atomic mass unit to meters per second, that's actually the speed of light squared. That's why. This is actually E equals mc squared. This is the m and this is the c squared.
That's crazy.
But it's in way different units at this point. And so essentially what we're doing here is that what you're trying to figure out, this whole binding energy, is the energy you get by making these things into an element. Because some of them, you can kind of think of some of the mass has been converted to energy, and because some of that mass, like in the case of helium becoming hydrogen, it's actually more stable as hydrogen than it is as helium. We gain energy from this reaction. This is the energy that powers nuclear reactions. And so what's interesting is that down at that end of the periodic table where hydrogen and helium are at the beginning, you can actually gain energy by fusing the nuclei together, which is what powers the sun. It's nuclear fusion. On the other end of the periodic table, you can actually gain energy by ripping the atoms apart. That's nuclear fission, because they'll be more stable if they're slightly smaller. That means somewhere in the middle, you hit nuclear wasteland. And basically what that means is at that point, once you reach that particular element, and there's one on that periodic table, then once you reach that element, either fusing or fizzing, once you reach that point, you can still fuse it, or you can still make it break apart, but it's not going to produce more energy than what you have to put in to do that, right? At that point, You can't really do fission or fusion and get energy out of it. It's only just going to be a hole. And that element is iron. Called it out to something. And that's the thing, like, if you're talking about like a star, like our sun, it's cramming mostly hydrogen making helium. But in the core, well, what's more dense, hydrogen or helium? Which one's heavier? Helium, because you got more stuff to do it.
I didn't think about that.
You guys, wait, what?
I didn't think about
But
that.
as the sun makes these heavier elements by fusion, what ends up happening is those heavier elements actually just stay in the center of the sun. And so it takes a little bit more energy to get these things to fuse, but it will fuse some of those heavier elements like lithium and beryllium. And what ends up happening is eventually the star will actually start to swell because of these elements inside of it. And so a star like ours will eventually swell up and become like what's called like a red giant. And theoretically, when our sun swells, its radius will go from its current distance to basically where the Earth is.
It's not good.
But what's happening there, one of the reasons why it gets bigger is because it starts to build up iron in the core. And as it starts to build up iron, it can't really fuse it. I mean, it will occasionally, but that's just going to take more energy. And so the thing has to end up swelling up in order to overcome this constant crush of gravity. And so whenever a star starts to build up iron in its core, that's the beginning of the end for the star.
Right.
Hooray, death. What is the nuclear binding energy of iron to the nearest mega electron volt? So this is just doing exactly what I just said. So you look at iron, go, okay, iron's got 26 protons. So we'll do that. We'll do 26 times our atomic mass unit for a proton, essentially. Then you do 26 minus 56, which is 30. Do that times your number of, times your neutron mass unit. Huh? 56. And then 26 minus 56 gives me 30. And then I subtract that number on the bottom, which says is 55.845. Now, the thing is like if they don't typically give you guys like a whole periodic table on the AP exam, you'll notice your thing doesn't have a whole periodic table. What they'll do is they'll give you like, just like a little section. You're like, these 5 elements. And so what they're trying to do is they're trying to just give you the relevant part, but they will include a couple of other elements that you don't necessarily need to make sure you actually know what the crap's going on. So one of the things I want to point out right now is that is an old periodic table, and I try to use like the actual new updated numbers. So if you're ever looking at, like say the notes and then look up at that periodic table and go, well, that's not the same, that one's wrong. Okay? I'm just telling you right now. Like that's why I keep looking up, I'm like, is that, okay, that's the right number. But I know that look, that's just so old. Like that's older than, it's been around longer than I've been teaching. So like when I started teaching here, that was just in my room. I was like, this is mine now. So you do this times this times this, minus 55.845. So I want you guys to understand where these numbers are coming from. Like this number, this point, or 1.00794 and 1.008665 is on your equation sheet. Okay. And a lot of times it'll just like give you like all of this stuff, like, you know, it just says like, oh, it just takes a little not screen time, but you know, just a little picture of iron itself with all the information in it for it. So you do that, you subtract, and then you multiply by this number. So when you subtract these two, we only get a mass defect of about 0.62, multiply by 931.49 mega electron volts per atomic mass unit. And we get 578.82 mega electron volts. Okay? That's the binding energy for iron, right? That's basically the energy you can get out by making it iron. So, as the atomic mass number increases, the nuclear binding energy increases because there are more nuclear bonds, okay? So basically, if you're looking at the binding energy per nucleon, so that would be taking that binding energy we just got and then dividing by the total number of things in the nucleus, so like that 570 whatever we just got, and divide by the 56, that will give you the binding energy per nucleon. Does that make sense? And so generally, as the atomic mass number goes up, this goes up to a point. You'll see this maximum right there. So at first, when you go from like hydrogen to helium, like that's a pretty good jump. And then helium to, was it lithium? Like that's a good jump, right? Basically, this you get tons of energy out by doing this, right? Another useful measurement is the binding energy per nucleon, which is what we're seeing here. And the line connecting points on this graph is called the curve of binding energy. And so notice that this is for atomic mass numbers. So like uranium is like uranium-238. So uranium is this guy over here. Okay? But notice there's a maximum right here just after 50.
Hi,
What's up?
can we ask these guys if y'all want a net gator? Just raise your hand and we'll come.
Yes.
Yes.
No,
Yes.
what?
Nah, everybody.
Yeah, no,
Everybody
everybody.
says yes and everybody here. All right.
They just took a second like,
Just
what?
waiting to see. All right.
As soon as one somebody said it, they're like, oh,
Okay.
good.
Thank you.
You're welcome.
Oh, cool.
Have another one now?
All right.
Now I gotta take a phone.
Thanks, Mr. Dupree.
No, no problem.
Y'all have a good day, guys.
Thank you.
Oh, you. No.
Yeah, oh, you. Was this open, Mr. Dupree?
No, I got one. That's fine. Thank you.
Uh-huh.
So, for those of you who don't know, Dr. Perry is the principal and the associate principal is Greenwich.
Oh, sorry.
Oh. So now, you know which one.
Wait a second.
Okay. Okay, so nuclear binding energy, cool. Fission versus fusion. So first of all, fission is where nucleus comes apart. Fusion is where we put it together. Pretty easy. If you can't remember fusion has less S's because they've been fused together. If two light nuclei can be joined together to make a single larger nucleus, the final nucleus will have a higher binding energy per nucleon. Because the final nucleus is more tightly bound, the energy will be released in this fusion process. And nuclear fusion of hydrogen to helium is the basic reaction higher than the sun. I said that. Nuclei with A greater than 60 become less stable as their mass increases. Okay? So anything past, 50, 56, 60, whatever, becomes less stable, right? So right there, right around iron, okay? Adding nucleons decreases the binding energy per nucleon. Like you can still do it, but you're just getting less energy out. Matter of fact, at some point it becomes more difficult to do it. So alpha decay is a basic type of radioactive decay that occurs when a heavy nucleus becomes more stable by ejecting a small group of nucleons in order to decrease its mass, releasing energy in the process. So this is nuclear fission. So nuclear fission is something that's down here, past iron, way past iron. If it can give up a chunk of itself, it will go closer to having more binding energy per nucleon, and that's what it wants to do. That's essentially everything's trying to roll downhill to iron. So when very heavy nuclei are so unstable, they can be induced to fragment into two actually lighter nuclei. So sometimes it undergoes like one of these alpha decays or something, but sometimes literally the whole atom will split, right? And then you'll have two different elements, but neither of which are like alpha or beta decay or something. It's literally just two, just like a nucleus just splits in half. Does that make sense? Yeah. So alpha decay. So if you're looking at your binding energy for nucleons and your atomic mass numbers, so this is alpha decay. Basically, alpha decay occurs with all of these elements that are past 60 here on the periodic table. So anything past 60 has the ability to do alpha decay to become more stable. Right? That's, won't necessarily do it, but has the ability to do it. So again, if you were to write alpha decay generically, you would say your generic atom X has A nucleons and Z number of protons. So if it undergoes alpha decay, you lose 2 protons, so 4 things on the nucleus, because alpha particle plus energy. The dark nucleus, which is much more massive than an alpha particle, undergoes a slight recoil, and so the energy released in the alpha decay ends up mostly as the kinetic energy of the alpha particle. So if you do this mass defect thing here, just that times c squared, you can really just calculate the kinetic energy of your alpha particle. So think of it like a bullet being fired out of a gun. The gun recoils and the bullet goes forward, but which one's going faster? The bullet. And so that's what's happening here. The alpha particle is much smaller than the parent nuclei, and so it's going to go way faster. So pretty much all of the kinetic energy ends up in the alpha particle, which is why they tend to go pretty fast. All right, strong nuclear force. So it's an attractive force between any two nucleons. It does not act on electrons. Again, neutrons and protons, which is why they stay in the nucleus. And electron might pass through the nucleus or something, but it's not affected by the strong nuclear force, so it doesn't care. It's a very short-range force, acting only over nuclear distances. So we see no evidence for the strong, or for either of these nuclear forces outside of the nucleus. Over the range where it acts, it is stronger than the electrostatic force that tries to push two protons apart. But again, a nucleus with too many protons will be unstable because the repulsive electrostatic forces will eventually overcome the strong attractive force, because the electric forces are weaker, but the strong force has a very limited range. Because neutrons participate in the strong force but exert no repulsive forces, the neutrons provide the extra, quote, glue that holds the nucleus together. Are we okay with that? All right. Let's get into it. This is the part where I'm actually going to answer that question about what the heck gamma is doing. And this will actually make a lot of sense, but we're going to go a lot more detail than is required. Okay? So don't freak out. Because I'm going to show you a lot of stuff, and to me it actually makes super logical sense why all of this crap is happening. But you're not going to be tested over it, and so it might be a little overwhelming to be like, I can't remember all. You don't have to remember all. Okay? So low Z nuclei, so low number of protons nuclei. Everybody with me? So this is basically where your number of protons is equal to your number of neutrons. So that's what that says. As the nucleus grows, the repulsive force increases faster than the binding energy, so more neutrons are needed for stability. Okay. So protons and neutrons have quantized energy levels like electrons. They have a spin and they follow the Pauli exclusion principle. And we haven't really talked about the Pauli exclusion principles. So, okay, let's get a little bit more quantum mechanical. So remember, the word quantum means it has a very particular number, right? It has a very particular slot. It's not just like, oh, it could be anything in the universe. We talked about electrons in their orbitals have very specific orbitals, right, around their atoms. And they have a spin, and they participate in the Pauli exclusion principle. What that means is the Pauli exclusion principle is basically like there can only be one thing in that atom that behaves like that. That basically, like, you know, if you're thinking about electrons, like in the very first orbital, how many electrons can you stick in there? 2. Because of the way the orbital is shaped, the only reason why you can have 2 is because one has an up spin, one has a down spin. They kind of match each other. But you can't have 2 electrons in there that both have up spin. One of them will get kicked out, right? It's the Pauli exclusion principle, right? Not all subatomic particles follow the Pauli exclusion principle, but the like protons, neutrons, stuff like that that you guys know of does. Okay, this isn't like some Bose-Einstein condensate crap. So what we can do is for electrons, we can if I said electrons here, all right, let's not look at this stuff right now. Pretend this is electrons. So if you have an atom that has electrons orbiting, right, it's got different orbitals, right, like shell 1, shell 2, shell 3, S orbital, P orbital, all that crap, right? And you guys know, hopefully, that in the first orbital, you can only have two electrons, right? And so you can have two because one can spin up and one can spin down. They come in pairs, right? How many electrons can fit in the second orbital? 8, right? 4 pairs of 2, right? So if I put 8 here, then I'd have, up, 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 and then down paired with each one, right? Now, here's the deal. We talk about, like, photons of energy can come in and hit one of these electrons and cause it to jump up to a higher energy state, right? And then it can stay up there at a higher energy state, then it'll fall back down and release that photon again, right? That's for electrons. Everybody get that? And then we talked about that if you give it enough energy, like a big enough photon comes in and hits this guy, it can give it enough energy to eject it from the atom, right? Or ionization energy. So first of all, notice that the energy is written from 0 to negative, because when it comes out, we consider it to have 0 kinetic energy, right? So anything above 0 is its actual kinetic energy, right? So in order to get electrons out, you have to put in some energy just to pull them out of the hole that they're in. Does that make sense? That's for electrons. Everybody okay with that? Now let's talk about what's going on here with neutrons and protons. It's basically the same thing, right? They participate in the Pauli exclusion principle. They have spin, they have upspin, they have downspin. And there are energy levels, just like there are orbitals for electrons, okay? We're not going to look at any of those shapes or any of that garbage. But it's in there, all right, in a very similar way. You know with me? As a result, so here we're just looking at low, Z nuclei. And so this is for neutrons and protons. And if you make a graph like this, where it takes a certain amount of energy, theoretically, a photon could come in of high enough energy, hit one of these neutrons here, give it enough energy to actually eject it from the nucleus. That is totally possible. Highly unlikely, but totally possible. Okay? Just like it could happen for electrons. The reason why it's highly unlikely is because, do y'all remember how much energy it took to, say, the one electron away from hydrogen? It's 13.6 electron volts. That's it, just 13.6. That's the easiest one to pull away. Okay? What's the scale on this? Mega electron volts. So in order to pull off like one of these guys, you're going to have to put in like 10 million electron volts. Not like 13.6 electron volts, like 10 million. So yeah, it could happen, but let's just say photons of that energy are very, very rare. Okay? Okay, that aside, you can see that they have energy levels just like the electrons. And just like the electrons, they want to fill from the bottom up to the top. Make sense? And they want to be down here in the lower energy levels because that requires less energy. And the only reason why this stuff has stuff in it is because this is full up. Make sense? Now, what this is trying to tell you is that for neutrons and protons at low Z nuclei, for neutrons and protons, these lines, these energy levels, are pretty close to the same. They're not exactly the same, but if you made a graph like this, they basically look parallel. Now, in truth, I think the protons are a little bit more stable than the neutrons, right? They're technically a little bit lower, but just a little bit. Are you okay with that? Let's go to the next part. So here, I have put the picture put in actual like neutrons and protons. So for this possible thing, this is carbon 12. That means it has 6 protons and 6 neutrons, right? 12 things in the nucleus. So it would fill up the bottom ones first, just like the electrons do. And again, they have spin, like upspin and downspin. So 2 go on the bottom layer, then 4 go on the next layer, and that's it, right? We got 6 protons and 6 neutrons. That's stable carbon 12. Got with me? Now, low Z nuclei have few protons, so we can neglect the electrostatic potential energy due to the proton-proton repulsion. what this means here is that once you put in more and more protons, what ends up happening is that these energy levels actually will start to spread out. Right? Whereas the neutron ones will stay closer together. Okay, because as you cram more and more protons in here, the less protons want to be in there. Does that make sense? Because they're all positive. But you can pile more electrons for the same number of protons. So here, this is just carbon. Everybody okay with carbon here? That's just nice, stable carbon. So, let's say that bismuth 12 and nitrogen 12 could lower their energies in a process known as beta decay, where a proton becomes a neutron or vice versa. So here it gives us B12. So B is boron, right? Does boron normally have 12 things in its nucleus? No, it normally only has 10. But let's say somehow boron is created, and it's got this number of neutrons, right? It still has 5 protons because it's boron. You know with me? But notice, because all these energy levels are basically the same, if I have, not 6, but 7 neutrons, well, I go 1, 2, 3, 4, 5, 6. 7 will be up here in this next energy level. Note that if it can fall down to this energy level here, which is over on the proton side, it's more stable. You all see that? And that's what it does. And when a neutron becomes a proton, it emits that positron in this case. Whereas over here, this is like nitrogen 12, so it has 1, 2, 3, 4, 5, 6, 7 protons, but only 5 neutrons. Again, this proton can fall down into the neutrons, and again, it will emit, I guess this one emits a positron, that one emits an electron. It'll fall down there to become more stable. Does that kind of make sense why they would even want to do this? Because I think alpha particles make sense. It's just like you have this atom that's so big that it just can't really stabilize itself, but if it sends up a chunk or maybe a whole half of it, it becomes more stable. But when it does that, when it breaks apart and sends off, let's say, a chunk of nitrogen like this, okay, this chunk goes flying off. But this particular chunk has 7 protons, but only 5 neutrons. So that's not really nuclearly stable. So then after a little bit of time, this thing will fall down over here and give off that beta particle to become more stable. Does that make sense? Now, when we get to high Z nuclei, you'll notice that these energy levels for the protons will start to spread out because they don't want to be near each other. So what you end up with is you end up with a lot more energy levels for your neutrons, which is why the higher elements have more neutrons in them, because even if they started out as protons, they can probably fall down into these slots and become more stable as neutrons. Okay. So again, it's all about these vacant energy levels, wherever you got the holes. So the net result, so here it says, if their neutron energy levels were vacant above the proton levels, the nucleus would lower its energy by changing neutrons to protons and vice versa. The net result is the filled energy levels for protons and neutrons is just about at the same height. Right? So overall, what happens when things are stable is wherever the stuff is filled to, it's filled to the same level on both sides. Right? If you have a bunch of stuff that's over here and not over there, well, then it'll get, kind of think of it like going downhill. All right. So, again, this is gamma decay, which we haven't talked about. If you have something, let's go back here. It's not bad. If we go back here, I said this could just randomly occur when just some chunk of it breaks off. Are you all with me? Well, what's interesting here is that there's nothing saying that when this chunk breaks off, all of these neutrons are in the lowest state. Maybe all of them were way up here when it broke off. So all of the neutrons might want to fall down. Does that make sense? Because they're just simply at a higher energy level. Like if you had a larger atom, you would have, well, neutrons all over the place, different energies. But in that one particular atom, like even if you think of something massive like uranium, only 2 neutrons are gonna be down here. When it breaks apart, those neutrons are either gonna be one side or the other. Does that make sense? This only has 2 neutrons, and those have to be somewhere. So let's say that it breaks off, and on the left part, that's where those 2 neutrons are. But on the right part, there's nothing in that hole. Do y'all see that? That by breaking it apart, it's immediately created a hole at the bottom. And so any of the neutrons above that don't even have to change from protons to neutrons. They just simply have to fall down into that hole. Does that make sense? And when it falls down into the hole, that is gamma. It's where you already have that hole, and nothing has to change to fall into the hole. It just has to fall into it, which is why gamma, nothing changes. Like a proton number and neutron number don't change, but energy is still released. Because again, the neutron is falling down into that lower energy level, which is now available, but it doesn't have to change. It just has to go downhill. So here, this is just kind of like, again, like your electrons. Like if your electrons are energized for some reason, if they fall back down to a lower energy level, well, they'll emit a photon. In this case, they will also emit a photon. But again, these are very large energy levels. So when a neutron or a proton falls down, it's only a gamma ray. And the thing is if you remember our electromagnetic spectrum, gamma rays were way, way, way on the end because they're the smallest wavelength, but they have the highest frequency because they have the highest amount of energy. And technically, some people call like super high energy gamma rays like cosmic rays or whatever, but you can call them that or you can just call them gamma rays, I don't care. But essentially, when it falls down, a nucleon makes a quantum jump to a lower energy level. The jump is accompanied by the emission of a photon, where the photon is usually equal to 1 million electron volts, which is why they only come out as gamma rays. Like you don't see like visible light photons coming out when a neutron falls down because it just doesn't have the energy, right? All right, so example 3. An apple is irradiated for 2 hours by a very strong radioactive source. Is the apple now radioactive? So here I've got my radioactive element, whatever, in here, and it's giving off radiation. Let's say it's gamma, whatever. It's giving off radiation, and we allow it, we have it boxed, so it only comes out basically this hole towards our apple. So we sit this apple right here, and we irradiate it for 2 hours. Let this process go on for 2 hours. Is the apple now radioactive? Yes? No? Depends on the kind of radiation. No, it's not radioactive. Because this thing is giving off like alpha, beta, or whatever, but that is the process of radioactivity. Once it gives it off, and it hits something, well, it's over with. This is actually a way to pasteurize food, is through radiation. Because if there's like bacteria or viruses on here, this has enough energy to kill them. It's like microwaving it essentially, except not, because the energy will just pass right through it. The reason why gamma rays and X-rays are dangerous is because they tend to pass right through your body, but they also tend to destroy things like DNA along the way.
I need that.
Now, like the apple kind of needs it if it wants to like grow into a tree, but if you're not planning on growing that apple into a tree, it doesn't matter.
Just eat it.
So phosphorus has a stable isotope of P31. That isotope P32 is a neutron-rich radioactive isotope that is used in nuclear medicine. What is the likely daughter nucleus of P32 decay? So if P32 is stable and P31 is stable, P32 is not stable, what does that mean?
Cluster 1, release.
That's going to decay. Well, what do y'all think? Alpha, beta, or gamma?
2, release.
First of all, you should see that gamma is not going to get you what you want, right? And it's most likely beta. So A32 isn't really a large mass number, so it's probably not going to be alpha. Does that make sense? And it's probably not going to be gamma because just proton falling down isn't going to get me closer to P30. Right? there's probably gonna be some type of beta decay. And so since it's neutron rich, it probably has more than one neutron, so that neutron's probably gonna become approached. Make sense? Oh, that's the left side. Nuclear radiation is a form of ionizing radiation. So the energies of alpha and beta particles and the gamma ray photons have energies that are much higher than the ionization energies of atoms and molecules. When they interact with matter, ionizing atoms and breaking molecular bonds. Ionizing radiation causes damage to your body by driving chemical reactions that would not otherwise occur. Ionizing radiation can also damage DNA molecules by ionizing them and breaking bonds, which can create a mutation or a tumor. So that is the. You don't need this, and you don't really need that whole thing that I went through on the energy levels. But I think that if you kind of understand that, it kind of makes sense why this crap is happening. Right? It's not just random, like, oh, just now it decides to be radioactive. Like, it's all just trying to become more stable. That's what it all boils down. All right? We don't go ahead and get out of here.